Have you ever wondered how your computer manages multiple disk I/O requests? It's all thanks to a process called disk scheduling. This is a technique used in operating systems to manage and schedule I/O requests for a disk. When multiple processes make I/O requests, only one request can be served at a time by the disk controller. The remaining requests need to wait in a queue and be scheduled for execution. This is a crucial aspect because the hard drives are one of the slowest components in a computer system. Let's break it down further with some key terms. First up is seek time. This is the time taken to position the disk arm to a specified track, where data is to be read or written. The goal here is to minimize the seek time to increase efficiency. Next, we have rotational latency. This is the time it takes for the desired sector of the disk to rotate into a position where it can access the read-write heads. Just like with seek time, we want to reduce the rotational latency. Then we have transfer time, which is the time required to transfer data. This depends on the disk's rotational speed and the number of bytes to be transferred. Finally, there's disk access time. This is the total time for accessing data, and it includes seek time, rotational latency, and transfer time. Now that we understand these terms, we can dive into the different disk scheduling algorithms. These include first come, first serve, shortest seek time first, scan and c-scan, and look and c-look. Each of these algorithms has its unique approach to managing and scheduling disk I/O requests. Understanding these terms is crucial to grasp how different disk scheduling algorithms work. First, we have the simplest disk scheduling algorithm, first come, first serve, or FCFS. Just as the name suggests, this algorithm operates on a very straightforward principle. The first request to arrive is the first to be served. Imagine you're at a bakery. The first customer to order a cake gets their cake first, regardless of what the next customer orders. The FCFS algorithm works in the same way. It's fair and simple to implement. Every request gets a fair chance, and there's no indefinite postponement. However, it's not without its disadvantages. The FCFS algorithm does not consider the current position of the disk arm, meaning it doesn't optimize the seek time. If a request comes in for a far-off sector of the disk, right after a request for a nearby sector, the disk arm has to travel a greater distance, which can slow down the overall process. While FCFS is simple and fair, it doesn't optimize seek time, which can be a drawback. Next, we have the shortest seek time first, or SSTF algorithm. This algorithm is all about efficiency. It selects the disk I/O request closest to the current position of the disk arm. The aim here is to minimize the seek time, that is, the time taken to position the disk arm to a specified track. Imagine a librarian in a vast library. Instead of going down the list of book requests in the order they were received, she chooses to first fetch the books that are closest to her current position. This way, she minimizes the time spent walking back and forth between the shelves. However, this approach has a potential downside. Requests that are far away from the current position may end up waiting indefinitely, a situation we call starvation. Just like the librarian might neglect a book in a distant corner, the SSTF algorithm might keep postponing a distant disk request. So, while SSTF can minimize seek time, it may lead to starvation for distant requests. Moving on, let's talk about the scan and c-scan algorithms, also known as the elevator algorithms. Imagine an elevator in a building. It starts from the ground floor, goes up to the topmost floor, serving everyone in its path, and then comes back down, again serving everyone. This is similar to how the scan algorithm works. In the context of disk scheduling, the scan algorithm moves the disk arm back and forth across the disk, serving all the I/O requests in its path. It starts from one end of the disk and moves to the other end, serving all requests in its path. Once it reaches the other end, it reverses its direction and starts serving the request from that end to the other. This back and forth movement is why it's referred to as the elevator algorithm. The advantage of scan is that it provides a more uniform wait time compared to the first come, first serve or shortest seek time first algorithms. However, it can lead to extra seek time if there are no requests at the extremes of the disk. Now let's talk about the C-scan, or circular scan algorithm. This algorithm is a variant of the scan algorithm. Instead of moving back and forth across the disk, the C-scan algorithm moves in one direction only. After serving all the requests in its path, instead of reversing its direction like scan, it jumps back to the beginning of the disk and starts serving the requests again. This strategy treats the disk as a circular list, hence the name circular scan. It can be beneficial in situations where a uniform response time is more important than minimizing total seek time. However, it may not be as efficient as scan when there are more requests at one end of the disk. So, in conclusion, both scan and cscan prioritize requests in the current direction of movement, but they handle the disk queue differently. Finally, we have the look and clook algorithms. These two algorithms are improvements over the scan and cscan algorithms we discussed earlier. They aim to optimize disk scheduling by reducing unnecessary movements, thus saving time and increasing efficiency. Let's start with the look algorithm. It's quite similar to the scan algorithm, but with one significant difference. It doesn't go all the way to the end of the disk. Instead, it looks ahead to see if there are any pending requests in the direction it's currently moving. If there are, it continues in the same direction. If not, it reverses its direction and starts serving the requests in the opposite direction. This approach minimizes wastage of seek time, as the disk arm doesn't need to go all the way to the end of the disk if there are no requests. Now imagine you've combined the best features of cscan and look, and you get the clook algorithm. The clook algorithm also functions similar to the cscan algorithm, but with the added efficiency of the look algorithm. It only serves requests in one direction, just like cscan. However, once it reaches the last request in its current direction, instead of going all the way to the end of the disk, it jumps directly to the closest request at the other end, just like look. This way, clook efficiently serves requests in one direction, avoiding unnecessary movement to the edge of the disk. In conclusion, both look and clook are efficient disk scheduling algorithms. They aim to reduce unnecessary movements and optimize disk scheduling. However, they aren't without their potential issues. For instance, there could be a delay in servicing requests if there are a lot of requests in one direction. Despite these potential issues, they are often chosen for their efficiency and their ability to minimize seek time. Look and clook efficiently serve requests in one direction, avoiding unnecessary movement to the edge of the disk. Now that we've explored these disk scheduling algorithms, you should have a better understanding of how your computer manages multiple disk I/O requests. We started with the first-come, first-serve algorithm, the simplest of them all, where the fairness of serving requests as they arrive has its perks, but the lack of optimization for seek time can be a drawback. Then we moved on to the shortest seek time first algorithm, which prioritizes the closest request for minimal seek time, yet this can lead to the unfortunate neglect of distant requests. Next, we delved into the scan and cscan algorithms, also known as the elevator algorithms. Scan works like an elevator, moving back and forth across the disk and serving requests in its current direction of movement. On the other hand, cscan, while similar to scan, has a unique twist. Treating the disk as a circular list, it moves the disk arm only in one direction, covering the entire disk surface for a comprehensive sweep. Finally, we examined the look and clook algorithms. The look algorithm, similar to scan, stops at the last request in the current direction, avoiding superfluous movement to the edge of the disk. clook combines the features of cscan and look, efficiently serving requests in one direction, much like a one-way elevator. Each of these algorithms has its unique features and differences, serving specific needs and scenarios. Understanding them not only gives you a clear picture of how your computer manages multiple disk I/O requests, but also empowers you to make informed choices when designing or working with operating systems and their disk scheduling. Remember, efficient disk scheduling is crucial for a computer's performance. So the next time your computer is processing multiple tasks, you'll know what's happening behind the scenes.